go step by step. So here is the outline of my talk. So first I will introduce the strong CP problem and the Axion solution to it, and then we'll explain this novel Murayama proposal from the beginning of this year, and also the associated problems which we tried to solve, and actually we could not solve them completely. So I will dedicate big part of my talk discussing these problems and basically why they arise, and finally conclude with some curiosity, which is a light and visible axion limit of this new proposal. But okay, let's see. So the strong CP problem is can be formulated as follows. So here we have the QCD Lagrangian, and this QCD Lagrangian has two sources of potential CP violation. So the first source is the complexity of the quark mass matrix, and the second source is the so-called theta term, so topological term. Actually, the physical CP violation parameter is given by the sum of this, let's say, bare theta term and the phase of the determinant of quark mass matrix, and this is called theta bar. And this theta bar contributes to CP violation observables. In particular, it would contribute to the permanent electric dipole moment of the neutron, as written here. And from the non-observation of this electric dipole moment of neutron, a very stringent bound is set on this theta bar of order of 10 to the minus 10. And basically, it's a problem because on the, let's say, natural grounds, we would expect this theta bar to be of order 1. And so somehow it's puzzling that there is apparently no CP violation in strong interactions. And here I just want to stress that this is only one part of the problem, because we also know that in weak interactions, CP actually is violated, and there is CP violation phase in the CKM matrix, which is order 1 parameter. So this is puzzling, and several types of solution to this problem has been proposed. Probably the most known one and interesting one is the so-called Axion solution to the strong CP problem. The idea here is to promote this theta bar parameter to a dynamical scalar field, the axion. So basically, theta bar becomes the axion divided by its decay constant. Now we have the dynamical Lagrangian, where this axion couples to GG dual, and the QCD generates potential for this scalar field, and potential is such that axion dynamically relaxes to 0, namely its vacuum expectation value is 0, and hence the theta bar is also 0. So what are the ingredients needed to solve, basically to implement this solution? It's basically new global U1 symmetry, so-called U1 Peccei-Quinn, proposed by Peccei and Quinn almost 50 years ago. So this is a global symmetry which is spontaneously broken at the scale Fa, implying that the axion is Nambu-Goldstone boson, but it also should be anomalous under QCD, namely the divergence of this Peccei-Quinn current is non-zero, and then so it means that there is a source of explicit symmetry breaking, implying that axion actually is not a massless Goldstone boson, but rather a pseudo-Goldstone boson. So what are the properties of this hypothetical particle? So the first is axion mass, which is generated by QCD, and can roughly be estimated as a lambda QCD square divided by Fa. so this can be computed also more precisely in the framework of chiral perturbation theory, and the state of the art is NN-Leo computation in KPT by Villadoro and Gorgetto, who estimate the axion mass to be 5.7 millielectron volt, assuming that Fa is normalized to 10 to the 9 GeV. So why this 10 to the 9 GeV? Because there are very stringent constraints from astrophysics, namely from cooling of supernova, which imply that if axion is light, namely is lighter than 500 MeV, so okay, here it would be, let's say, 5 millielectron volt, then Fa should be larger than 10 to the 9. So it means that axion is very light and very weakly coupled. And in this talk, following Murayama, we want to ask, can the QCD axion, which solves the strong CP problem behavior, at the same time evading all existing constraints? So this is the question we want to address here. And so this is motivated by this paper, which appears at the very beginning of this year by Hitoshi Murayama, which is called GeV-scale QCD Axion. And indeed, he says, we study the possibility that this Peccei-Quinn symmetry is broken not at 10 to the 9 GeV, but below QCD scale. And we find that QCD axion indeed can have mass above GeV, and maybe it is hidden among already observed eta pseudoscalar resonances. So he argues that this proposal actually evades all accelerator and astrophysical limits, but, and this is a big but, the most significant constraint, as I will try to explain, is the mass splitting between the charged and neutral pion. So we got very much interested by this work of Murayama and started to think and to work on it, trying to address this problem in red, which now I will introduce. So the main idea here is to have U1 Peccei-Quinn non-broken all the way down to the QCD scale. And then this U1 Peccei-Quinn is broken only after chiral symmetry breaking, so only once quarks condense. So this is a rather kind of drastic difference from the standard QCD axion scenario, because the scale of Peccei-Quinn symmetry breaking is very low. And how can it be implemented? So Hitoshi Murayama, he proposes a model in which he introduces a new complex scalar phi, having a Peccei-Quinn charge +1, and the only standard model fermion charged under Peccei-Quinn is a right-handed up-quark, and it has charge -1. So now we write the QCD Lagrangian, let's say above the QCD scale, lambda QCD. Since right-handed quark is charged, we cannot write the mass term, because left-handed quark here by assumption is not charged, so up-quark is massless. So down and strange the standard story here. And then we have kinetic terms and potential terms associated with this complex scalar, and a new Yukawa interaction between phi U left, U right, which respects Peccei-Quinn. So mass term for the up-quark, as I said, is forbidden by this U1 Peccei-Quinn. However, when chiral symmetry gets broken, the quarks acquire a condensate, chiral condensate. So this generates a linear term in the potential for phi, which in turn induces a wave. And so the Peccei-Quinn gets broken only after chiral symmetry breaking. So once phi acquires a wave, also we can, from this Yukawa interaction, have non-zero up-quark mass. So this is a proposal by Murayama, And so in what follows, we will generalize it, but then first I generalize and then I explain the problems with this proposal. So then we will consider generalizations in which we assume again that we have only one complex scalar phi, but now the up, down, and strange quarks, actually all of them can be charged with a charge minus nq. And then the effective Lagrangian above lambda QCD and below electroweak scale now has this form. So we have the standard kinetic term for gluons and quarks, theta term for gluons, and then the standard terms for this phi scalar. And it is convenient to write the Yukawa interaction or the mass terms in this way here. So let me explain a bit better. So what is this MQ? If the charge of the quark is 0, then MQ is the standard mass Lagrangian parameter, as in, let's say, in the standard QCD. However, if NQ is bigger than 0, then it is a rather Yukawa interaction. So indeed, in this Murayama model, for example, we have Nu is non-zero, is 1, and then we will have a Yukawa interaction for up quarks, while for other quarks we have the standard mass Lagrangian parameters. In what follows, we assume that the quadratic mass of the scalar is bigger than 0, so we don't want to have the standard spontaneous symmetry breaking mechanism. We want U1 Peccei-Quinn to be broken only by QCD chiral condensate. So only once quarks condense, we will have the spontaneous breaking of U1 Peccei-Quinn, which will induce the wave for this field phi. Also, this U1 Peccei-Quinn should be anomalous under QCD. This requires the sum of the charges of the quarks to be non-zero. Indeed, the generator of the Peccei-Quinn symmetry should have a non-zero trace. Finally, renormalizable models in this language, they correspond to charges either 0 or 1. Because if charge is bigger than 1, we will have non-renormalizable interaction, for example, of this type, phi square, q left, q right, so it's dimension 5 interaction with a certain new physics scale, which actually, as we will see, will be very low. So in what follows, we will focus mainly on renormalizable models. So in this language, the Murayama model, or as we can call it, massless up. Massless up here means massless before chiral symmetry breaking. So it corresponds to this assignment of charges, and U is 1, everything else is 0. And similarly, we can have massless down, massless up and down, where both up quark, down quark are charged under Peccei-Quinn, and finally also massless strange. So these are representative models. And so this is the Lagrangian region above lambda QCD. However, once chiral symmetry, so below lambda QCD, it's better to write a chiral Lagrangian in the presence of external Peccei-Quinn field phi. And it is written here, so the standard terms for phi and the standard terms in the chiral Lagrangian, so the kinetic term and the potential term. Finally, this term in the bracket is a proxy, let's say, for it arises from the axial anomaly, and this is needed to solve the strong CP problem. So here the U is the meson matrix, so we have the octet of the pseudoscalar mesons. We also keep eta prime because of its special role in the axial anomaly story. Note that both this meson matrix and the quark mass matrix, they transform in the same way under the chiral symmetry, U3 left times U3 right, and this precisely allows for this potential term here. Okay, so now in this Murayama proposal, quark mass matrix actually depends on this new scalar phi, and in general for generic charges it is written here. Again, to make an example, in the Murayama model, Nu is 1 and D 0 and S 0, then the quark mass matrix is like this. So here we have Yukawa interaction, and then standard MD and MS. So spontaneous symmetry breaking of U1 Peccei-Quinn is controlled by the condensate. Indeed, so this induces the linear term in the potential. Then we can solve that at pole condition, basically to find the minimum. And this leads to the following relation between the, let's say, decay constant of this field phi and its mass, which is written here. So as you can see here, actually they are inversely proportional, and everything is controlled by this F pi and B0 precisely the quark condensate. Okay, so now what is about spectrum? So what are the masses of this phi? Phi will have two components, either real part or imaginary part, or we can work in the so-called polar or exponential parameterization. So we will have the radial component and the angular component of the phase. So now the minimum of the potential should be in A equals 0, because we want to solve this strong CP problem, and also sigma 0. So then we solve this pole condition and find that there is a relation between M phi square, F phi square, and the quartic coupling lambda. So as I already mentioned, I want Peccei-Quinn to be broken only by chiral condensate. So then I need to require that the mass of this scalar should be bigger than 0. So this leads to a relation between F phi and lambda. So in particular, you can see in Murayama model, so to have a large F phi, one needs to have a very tiny lambda. If lambda is of order 1, also F phi will be, let's say, a GeV or even a GeV-scale. And then, so neglecting the quartic, so we can, let's say, for simplicity, neglect the quartic, then this pole condition simplifies, and we arrive at the following relation between the mass of the scalar and the mass of the quarks charged under Peccei-Quinn. And as you can see here, actually they are inversely proportional. So for example, if I take the lightest quark, as in Murayama model, the up-quark, I have these values. So M phi is roughly 2 GeV times Yukawa coupling. So if Yukawa coupling is of order 1, then the mass scale here for this phi is at around, let's say, 1 to GeV, while the decay constant is at MeV scale, so it's 3 MeV. Okay, so then we can have, so we have the radial mode, we can compute the mass, so it's simply the mass of phi square, and in the presence of lambda of the quartic, there is a correction. So we can estimate the mass of the angular mode. However, here the story is more complicated because A is pseudoscalar and it will mix with the pseudoscalar mesons, in particular pion, eta prime, as I will discuss in the next slide. But the estimate, so in the first approximation, the mass of this would be axion, again is M phi square, plus correction proportional to lambda. So you see that actually the splitting between the mass of the CP even and CP odd modes controlled by this lambda. So if quartic is 0, then the scalar and pseudoscalar modes are degenerate in mass. The actual value of MA, as I will explain in what follows, depends actually on the model. So as you can see now, so in this Murayama model, so axion would be a GeV-scale with very, very small axion decay constant, which is smaller than F pi. So actually this A looks very, very different from the usual axion, and so one asks, where is it? So where are these new degrees of freedom? And these new degrees of freedom, which are coupled to QCD, as Murayama speculates, actually maybe they are already discovered, and maybe they are hidden among known hadronic resonances. In particular, now if I fix this Yukawa coupling to 1/2, then masses are roughly would be A, corresponding to this resonance eta 1295 with a mass of, let's say, 1.3 GeV, and sigma would be its scalar companion, also with a mass roughly 1.3 GeV. And so this is somehow very interesting that maybe, so if this model works, maybe the QCD axion actually is not very light, but maybe it's a GeV-scale and maybe is already discovered, no? So something rather revolutionary here. So of course, in this case, axion cannot be dark matter because it decays fast, mainly hadronically, and here are the estimates for its decay width. However, okay, so this proposal is rather revolutionary, I would say. And of course, one needs to examine it clearly, so closer, to see if there is any problem associated to it. And the first thing to look at, as Murayama also does, is to see the mass matrix for pseudoscalar mesons. So this is the mass matrix in the basis of axion, or would-be axion, pion, eta, and eta prime. So this block, 3x3 lower block, is the standard KPT, let's say, block. And then we have axion mass parameter and the mixing between this axion and pseudoscalar mesons. So then what we need to do, we need to diagonalize this mass matrix to find the eigenvalues. And actually in the limit where f phi is much smaller than f pi, it can be done analytically. And what one finds that actually the mass of the neutral pion gets a negative shift with respect to its, let's say, standard model value, while of course charged pions, they don't mix with this new neutral state, so their mass is unaffected. Then one can estimate the difference between mass of neutral and charged pions in terms of the quark masses and these charges. And what one finds in Murayama model, that the result is minus 0.15. So it's 15% negative shift in Murayama model. So is it bad? Yes, it is, because experimentally we know that the difference between neutral pion mass and charged pion mass, the relative difference, is 3%. And this 3% actually entirely comes from electromagnetic splitting. So this new mass splitting is very problematic, because actually we not only should aim at this 3%, but actually we should aim at the error in the estimate of the electromagnetic mass splitting, because electromagnetic mass splitting is under good control, and also it actually is estimated on the lattice. So this is the main problem with Murayama model. So how can one try to solve it, or maybe to evade or to avoid it? So what Murayama himself mentions is the so-called Kaplan-Manohar ambiguity. So let me try to review it. So for some time, let's say from 80s till maybe beginning of 2000, the possibility that the up-quark is massless was not obviously ruled out. And why it was the case? Because actually mass ratios between up-down, strange down can be extracted from fit to pseudoscalar meson masses and KPT. So at leading order, Weinberg derived 50 years ago the relations, they are written here, and indeed, so you see that m up divided by m down is something non-zero, so at leading order, no, up quark mass cannot be zero. However, as was pointed out 40 years ago by Kaplan and Manohar in this paper, there is potential ambiguity at NLO, and roughly it goes in the following way. So the quark mass matrix and this combination, so apparently strange combination, transform in the same way under the chiral symmetry. So this strange combination, actually it can be shown that it corresponds to a certain operator in KPT expansion, operator of order of momentum to the fourth, so which is written here is a double trace minus trace square. And this Kaplan-Manohar operator is Dress's Legion order spurion, which is quark mass matrix, and the net result that actually the up-quark mass is rather, let's say, this Legion order contribution plus some correction which is proportional to the product of down and S masses. And then, so if we identify the physical up-quark mass with this mu kappa m, then let's say call bare mu can be 0. However, then this Kaplan-Manohar correction provides a non-zero physical mass for up-quark. And then Murayama suggests to maybe play with this Kaplan-Manohar ambiguity. Then the full quark mass matrix, including this Kaplan-Manohar correction, has this form. It does not, this Kaplan-Manohar does not modify the tadpole condition, but allows for reduced up-quark mass, let's say bare up-quark mass. Then we can write it as a physical quark mass divided by some number r, where we identify this mu Kaplan-Manohar with the lattice value, and then play with this r. So to play with this r, now we need r of order 5 to match experimental value, and this is what Murayama says, and his point of view is very conservative, because he says that we just want to decrease the splitting down to the observed value. However, as I mentioned, actually this observed value comes entirely from electromagnetic corrections. So then we need to match the lattice error of electromagnetic contribution, which is of course much smaller. This implies that we need R of order of 200. And note that the R infinity corresponds to massless up-quark, which is ruled out by lattice. So here the take-home message that maybe one can play with this Kaplan-Manohar ambiguity. However, in order to match the experiment, we really need very high values, which would imply the massless up. So here is the caveat that the standard results, they assume in the lattice simulation, they assume the standard model. So they don't assume this new phi field. So if one wants to study it seriously, one would need, on the lattice, one would need to redo the lattice simulation, including QCD with this new scalar phi. Okay, so then let's take a look at the alternative models without this Kaplan-Manohar ambiguity. This is what we did in our paper. So what happens if I charge both up and down quarks with a charge 1? Then this splitting again can be estimated, and there is improvement of a factor of 2. So now we are down to 7%. However, 7% is still very large. So as I said, we need less than 3% to match the experimental value, and even less to match the uncertainty on the electromagnetic contribution. Note that here this Kaplan-Manohar story would not work because this phi field appears also in the correction, since MD now is also given by this field phi. Another suggestion is to give different charges to up and down quark. For example, charge 2 to up quark, charge 1 to down quark. And then indeed we apparently almost cancel this splitting. So maybe one here says, very good, I found a model which works. So note here it's accidental cancellation due to the fact that the ratio of down and up quark masses is approximately 2. However, this theory would be problematic because, as I mentioned in the beginning, the charge greater than 1 implies that we have an effective field theory with a cutoff, which here one can simply estimate the cutoff, and I find the cutoff at something at 10 MeV. So I would need some new states which couple to QCD at MeV scale. So it's clearly something very problematic because we don't observe anything at MeV apart from, let's say, the quarks. Okay, the other try is to charge only strange quarks. So now so we don't touch UD sector. So indeed we preserve SU2 isospin symmetry as in the standard chiral PT, chiral perturbation theory. So pion mass splitting is okay. However, this model is also, it comes with associated problems. So the first problem, remember I told you that the phi mass and the mass of the quark, they inversely proportional. So now this parameter would be roughly, let's say, 0.3, 0.4 GeV. So it becomes already problematic given in particular astrophysical constraints, also meson decays, like d-meson decays to the axion and pion. And also here effectively this problem of the mass shift is shifted to the eta sector. So now we have 15% correction in the splitting of the let's say of the mass shift of the eta meson, which is less precisely known, but still 15% is actually a lot. Okay, so we also tried alternative models where we introduced two complex scalars, phi u, phi d, with different charges. We did a scan of this. Now the mass matrix becomes 5 by 5, and somehow what we find, actually we did not find a model which has both new pseudoscalar states at GeV-scale. So somehow one of the states comes light, so it's the MeV, and then this is not good. So, and this is an agreement with these EFT considerations I had before. One can even consider kind of a desperate attempt to introduce a Peccei-Quinn neutral scalar, just to make pi 0 heavier. Okay, so after this list of fails, one sits and asks, so why is it so hard or so difficult to make this, say, Murayama proposal work? So what are the general lessons we learned so far? So one may rely on this Kaplan-Manohar ambiguity in the NLO KPT Lagrangian. However, as I mentioned, it's better not to have very large parameter R, because then effectively one ends up with a standard model massless up solution, which is ruled out by the lattice, by caveat by the standard lattice. One would need to find models where the spin is accidentally restored, as in the 2-1 model, which however has a very low cutoff. Also, if one is able, one should perform, or if one is interested and is able, one should perform a new lattice simulation QCD plus this new scalar on a lattice. However, since I am not able to perform lattice simulation, I go for EFT consideration. So notice that this M phi in Murayama's story is roughly at GeV-scale. And so we have, even if mild, separation of scale between the mass of this phi and QCD scale. And so what we attempt to perform a kind of EFT expansion to gain further insight on this story. So the setup is as follows. So we have these new degrees of freedom, say between 1 to GeV, to hide them in these hadronic resonances. So we have heavy Peccei-Quinn invariant sector coupled to light quarks. And then we will match at the scale of m phi this theory to a chiral theory, which somehow will also be Peccei-Quinn invariant. So is a bit different from the standard chiral expansion, because now we will also search for the operators which both preserve isospin and also chiral and also Peccei-Quinn symmetry. So in this chi-pt, we will have two spurions. So the first spurion is similar to the standard story, is the quark mass, which, however, now will have some zero eigenvalues for quarks which are charged under Peccei-Quinn. And the second spurion is the matrix of couplings of this new heavy axion to light quarks, which is written here. So in what follows, I assume that only either U or D or both are charged, and I leave S to be neutral under Peccei-Quinn. So now these are my building blocks. I try to build an effective chiral Lagrangian, which also respects Peccei-Quinn symmetry. So in this Lagrangian, the first term will be the usual chiral Lagrangian, taken now as an input this reduced quark mass matrix, and the second term is the tower of operators, which I get integrating out this phi field. So we did this exercise, and what we found that the first non-trivial operator in this tower of new operators respecting Peccei-Quinn appears at order p to the fourth, and it has this form. So trace of this I dagger u multiplied by trace I u dagger. So notice that this operator is manifestly chiral invariant and Peccei-Quinn invariant, because both I and U, they transform exactly in the same way under the chiral symmetry, and they transform also in the same way under the Peccei-Quinn symmetry, where now the generator is basically the charges of U and D quarks. So what are the effects of this new operator, which appears at p to the fourth? So it can be shown that it precisely controls the splitting between the neutral pion and the charged pion. So the expression is here. So you can see now, so to make this splitting zero, or at least very, very small, we either need this accidental cancellation conspiracy between quark masses and the charges, or we need to switch off this operator, but there is only one operator, and notice that this operator breaks isospin while preserving Peccei-Quinn. So in the Murayama model, one can perform the matching, and one finds this relation here, so it's clearly non-zero, and this is why it creates a problem. So notice that also this operator will affect PP scatterings, pion scatterings, which are very well measured, actually. So then one can go on, and in the next order in this chiral expansion, one finds operators with two derivatives, O2 and O3, but as long as the chiral expansion holds, actually these operators, they cannot cancel the effect of the leading p to the fourth operator. So basically this is to say that there is nothing to tune this leading operator against. So this is the structural obstruction, and in this EFT language, so it's clear why the attempts we did with the renormalizable models, why they don't actually work. So before going to the conclusions, let me spend a couple of minutes on this curiosity. So of course the natural somehow setup where this M phi is at GeV scale, as I said, and F phi is at MeV scale. But notice that also this Murayama model admits a limit in which F phi is large and M phi is small. So it would be like more similar to the standard axion. So indeed, in this limit, we find that the pseudoscalar has the standard QCD axion mass expression, where now Fa is identified with Fi divided by the sum of the charges. So in my Murayama model, it would be simply Fi. However, as I mentioned before, this requires a tiny quartic, because if I want to have a phi large, then the lambda should be very small, with my requirement to have Peccei-Quinn broken only by after chiral symmetry breaking. And the problem with this invisible axion limit is as follows, because differently to the standard story in which radial mode is very heavy and integrated out, in this proposal CP even radial mode also becomes light, and actually one can derive a limit on the mass of this sigma mode, which is roughly at the level of the pseudoscalar. And there are very strong stringent constraints from fifth force experiments, basically on the forces mediated by a scalar between nucleons. And here is a curiosity, actually evading these constraints would require Fa, let's say, of the Planck scale, which in turn imply insanely tuned value of quartic. So basically, to conclude here, there is this curious limit of invisible axion. However, it also does not work because of these fifth force constraints. So, okay, conclusions. So, we found this proposal very interesting. So, in a sense, it can be viewed as a deformation of a massless up-quark solution to the strong CP problem, in which now we introduce a new operator which contributes to quark mass matrices. This operator controls, as I tried to explain, pion mass splitting. Setting its coefficient to 0 would recover precisely massless up. However, it is excluded by the lattice. Notice that this limit corresponds to the decoupling of phi field, because indeed, if the quark mass becomes 0, the mass of phi becomes infinity. So it's precisely decoupling limit. So what one would need to do to save these massless up deformations? So one would need to have models with accidentally small mass splitting, but having finite mu. We tried to design these models. Despite some partial improvements, unfortunately, we were not able to find a good model. Perhaps a final word on this story would require an updated lattice simulation of QCD enhanced by this new Peccei-Quinn field phi. Okay, so I think I stop here. Thank you for the attention. If there are any questions, of course, I will be happy to take them.
Question from the audience? Someone raised the hand. I don't remember who. Any questions? Question from the audience?
Just a comment. I'm glad to see. Antonio, please, can you mute yourself?
Let me see. Yes, Alfonso?
I'm. Can you mute, because when you are on mute, I hear my own voice. So thank you very much. I'm glad to see that new physics doesn't mean necessarily high energy physics, and it doesn't also mean electroweak sector. So I'm glad to see that there is interesting physics that can be done in the QCD sector, and I think it's important to pay attention to that.
Yeah, thank you for your comment. Indeed, so we got very much interested in this Murayama proposal now, because it seems that maybe, first we thought that maybe the QCD axion has already been discovered and is just hidden among these known hadronic resonances. Of course, all these Lagrangians I wrote here, and also which are written in Murayama sector, they should be viewed as theory which applies above, let's say, QCD scale, but below electroweak scale. Then one would need to search for UV completion, and Murayama in his paper he proposes some UV completion to make this theory also SU2 invariant. We did not go there because first we wanted to address this structural problem with the mass splitting of pions, and till now it appears to be actually the main problem. And as I said, perhaps one would need a new lattice simulation to have a final word on it.
Non-perturbative sector are hard.
Definitely, yeah, indeed. And my collaborators, some of them, they talked with lattice people, and I think there was some mild interest in performing the lattice simulation, but of course lattice simulations, they require a lot of time, and so it should be something where one also should be interested to invest your time into. So, but if anyone finds a way out from this pion mass splitting problem, we would be very much interested to know this. Okay.
Any more questions? Arsenii had a question. How you analyze the implication, for example, in the axion decaying to two gluons or to two photons? Because there can also be constraints in the from Titov decays.
Yeah, so basically we did not look at it in much detail, precisely because first we wanted to address the big problem. But if the big problem, I mean the mass splitting, were solved, then one would need to study in more detail the decays of these new degrees of freedom, which appear at the GeV-scale. Here they are mainly decay hadronically, and in a sense, there are already a few studies, not of QCD axion, but of ALP, GeV-scale ALP, where people studied in detail different decay channels, and then one would need to look at it in more detail. As I said, we did not do, so we did only some estimates. Also, Murayama, he does some estimates, because I think before looking into this in detail, one would really need to solve the big issue of this proposal.
Thank you, Arsenii.
Okay.
Any more questions from the audience? Okay. Any more questions from the audience? If there are no more questions, we thank Arsenii for the very nice and very complete seminar. Thank you so much, Arsenii.
Yeah, thank you for listening. It was a pleasure, and I'm happy I resisted without electricity. So, but hopefully it will come back.
Let's hope that it will come back soon.
All right, thank you very much. So I stop sharing.
Thank you so much,
and
Arsenii.
have a
Thank you so
good
much.
afternoon.
Bye.
Bye bye.
Thank you so much. Bye-bye.
Bye.